In this video, I wanted to look at the simultaneous diagonalization of two Hermitian operators, which sounds like a lot. So let's break it down. So I'm looking at the simultaneous diagonalization of two Hermitian operators. Okay, so if we just break it down into each of its individual parts, we're always interested in Hermitian operators because the operator is actually equal to its adjoint, but also we're looking to be able to diagonalize these operators, because once you diagonalize the operators, then those diagonal elements are basically the eigenvalues. So basically what I'm looking at is in the book, Theorem 13, which says that if I have two commuting Hermitian operators, we can call them omega and lambda, then those two commuting Hermitian operators, we should be able to find a common basis for them so that both of them get diagonalized. So we're looking for a common basis that diagonalizes both. Okay, so let's take a look. Basically, we'll take our two Hermitian operators, so capital omega, which operates on this eigenvector omega sub I, which will give us the eigenvalue omega sub I times that eigenvector, the original eigenvector. Now, if we look at the product, so we take lambda and the operator omega, and we operate on our eigenvector omega sub I, then first omega operates on the eigenvector, so we get lambda times the eigenvalue omega times omega sub I. And then now omega sub I, the eigenvalue, we can pull out front, and so we get omega sub I lambda times the eigenvector omega sub I. Which if we so if we look at it, we could get the same exact result if we use the commutation relation. So the commutator of lambda and omega is lambda times omega minus omega times lambda, and if they're commuting, then we would get a 0. So basically, if we look at our original operation of lambda and omega operating on this eigenvector, that would be the same thing as instead operating with lambda first, then omega second on the eigenvector omega sub I. So this should be equal to our previous result, which was omega sub I lambda times the eigenvector omega. Okay, so basically what it looks like is that omega sub I is the eigenvector, the eigenvalue of capital omega, that operator operating on the eigenvector. And it's also the eigenvalue of the state, that is lambda having transformed the eigenvector omega sub I. So you can think about it, those two ways. Omega operates on the eigenvector omega sub I. and then you get this eigenvector omega sub I. Or you can think of the state as first, lambda operated on omega sub I, and then when omega operates on that state, I get this eigenvalue problem of the eigenvalue returning the original state back again. Okay. So that means that, so one more step, and that is if we let lambda operate on the state omega sub I, and if that is an eigenvalue problem, then we would get the eigenvalue lowercase lambda sub I and the vector back again. So basically what that means is this eigenvector omega sub I is it's an eigenvector of both operators. It's an eigenvector of the operator capital omega, and it's an eigenvector of the operator capital lambda. And so therefore, what we're looking for is a diagonalization of both operators, capital omega and capital lambda, a diagonalization that shares this same state of omega sub I. So in the next video, what we'll do is we'll look at an example where we go over finding that common basis for these two the two operators, capital omega and capital lambda, working on this eigenvector, a common eigenvector.